Okay, folks, so I said I was going to start this particular video with a video of a Rube Goldberg. This is not a competition. This is a person who obviously does this for fun. So it's about 2.5 minutes. We might stop it, but we might not. So I'm just going to start this video and we can watch it through and I will talk about it as we go. So it all begins, if you're watching, when he puts down his glass. Now, each time things move, it's a transfer of energy. Okay. And the name of this is the cake server. So this is mechanical. Here's your solar energy. There's heat, because now it's going to melt the butter. So that's a type of heat energy. As it's moving, that's mechanical energy. So this is how, again, things keep moving, but they transfer each time they hit a new spot. So now we're transferring again. Here's again the heat energy, which is going to actually burn the cord. It's not losing energy in any of these scenarios. It's not creating energy. It's transferring it. So the whole idea is he needed to serve a piece of cake to himself. And he all began when he actually put his glass down. When he put his glass down, that was the force that began the energy movement of all of those objects. So I think it just puts into place a little bit what energy transfer actually is. The only time that energy was obviously created or destroyed really didn't happen, right? So it continuously moved. And that's what the example would be when we talk about a transfer a different type of energy. Energy changes, converts differently, but it's not used up and it is not destroyed. It is not created. So metabolism is what's happening inside those cells. So when we think of metabolism, we think of a big picture like my metabolism of my body or the digestive metabolism. What we're really talking about is metabolism within each cell. So that's the sum total of all reactions that are occurring in the cell. Sometimes they do move more often than not. So some cells are going to have more reactions than others. And again, that does have to do with time, length, age, the cell function. So when we talk about reactions, we're talking about particular pathways, catabolic versus anabolic pathways. Now, catabolism basically is breaking down. So taking a larger structure like this big stick and breaking it in half. Or my other example was having a big carbohydrate molecule and wanting to break it down into smaller molecules such as glucose so our body can use it. Now, the opposite of that is anabolism, where we're taking small little structures. So maybe we have a couple of glucose molecules, and when we put them together, we're building them up, we are making a larger molecule. So let's look at this. When we talk about actions that are requiring energy, we know when we contract muscles and relax muscles, we need some type of energy. So endergonic reactions require net energy, and that's anabolism, the ability to build an energy molecule. So when we're doing contraction, so here we kind of curled our arm up, we are creating the fact that we need a required net energy for this to happen. On the opposite side, our triceps are relaxing, and so that's basically a catabolic reaction. We're giving off energy. And then opposite here, when we kind of, again, straighten our arm, which we call extension, out. Exergonic reactions give off a net energy. So this is catabolism, where again, we're breaking things. So when we make things smaller, we're giving off energy. And that energy is important because our body is going to need to use that, or our cells are going to need to use that. So we can have some different types of work within our cells. We can have mechanical work, transport work, and chemical work. So mechanical work is most obvious. I think we're talking about mechanics, right? Movement. So here it might be muscle contraction, movement of cilia, generating cell movement. So movement of sorts, mechanical work. Transport work is just as it is, kind of movement across within the cell or across that plasma membrane. So kind of working to pump substances across the membrane or bringing them into. So it's really kind of transport. Think of what transport means, moving things around. Where chemical work is really the conversion. The chemical pushing or endergonic reactions where we make polymers into monomers. So we take the big structure, right, like a big carbohydrate, like I said, and break them down into smaller glucose, so monomers. So we have lots of types of work. Mechanical work is probably not the most important, but that's what we think of when we talk about energy specifically. So the energy we're talking about within our cells is ATP and what we call an energy coupling. ATP stands for adenosine triphosphate, which means that we have 3 phosphate molecules, tri. It's a very high energy molecule and it's made from ADP and a phosphate molecule. Now ADP means that there are 2 phosphates, so it's adenosine diphosphate, and then the extra molecule would be over here. Obviously, if we put these together, so we are making 2 smaller molecules into a bigger molecule, we would have 3 phosphate, okay? So it's a coupled reaction. When we're talking about making ATP, we need to have energy, obviously, to make that ATP. So energy is released when it's broken down to donate to work. So if we kind of look at this visual here, we have to have a little ATP, right? So we have to have ATP. And when we add ATP in a water molecule, so water molecules are important because they are called hydrolysis, okay? So hydrolyse is the end. Lyse means to cut something. So when we add water to this, we call this hydrolysis, and when we do that, we take this ATP and we make it, okay, ADP phosphate. And so energy, because we kick off that last phosphate, is used for cellular work, okay? So this is important. When we lose the ATP, when we have ATP, excuse me, and we lose that 3rd phosphate, that's when energy happens, okay? So when we lose that 3rd one. And we only do that because that water molecule separates it. Now, ADP has some structures here attached to, so it has an adenine, and it actually has a sugar molecule. I'm just writing S for sugar. And then it has 1 phosphate, and then a 2nd phosphate, and a 3rd phosphate, triphosphate. But what happens is because of their polarity, this last one basically doesn't like to sit with the other 2 because of their polarity. And so when it breaks off through hydrolysis, so when this comes in and splits them apart, this guy bounces out and he does all of the work. So when we do that, then we have ADP and then a phosphate, inorganic phosphate, kind of hanging around. We can easily build this back up with energy from the catabolism, and then we get back to ATP. So it's a cycled reaction. So here is the actual physical structure of ATP, what it molecularly looks like. Here is our adenine, which is a 2-ring. Wonderful structure, and it's bonded to a ribose, which is a type of sugar, and then the ribose bonds to each one of our phosphates, so our phosphate groups. So again, here's that 3rd phosphate that does not like to be hanging around with the other 2, so he easily can bounce off and leave, and when he does, that creates the energy. So if you look at this structure and kind of think about back to our macromolecules, we have carbohydrates, proteins, lipids, and nucleic acid. Based on this part of the structure primarily, we have what we call a nucleic acid. So ATP can also be a nucleic acid. The example I gave in class that I think is really important was that there's 3 phosphates. And so let's say there are 3 kids sitting on the bus, and those seats are meant to be, at least when I was back in my day, so when I was younger, we're meant to have 3 kids in each seat. you had a kid near the window, which happened to be this phosphate, this poor kid in the middle being squished, and the third kid that's hanging off the seat, basically. He's got one cheek on the seat and the other cheek kind of hanging in the aisle. And so he's not very stable, and there's not enough room for him. And so what happens if the bus hits a bump or turns a corner just right, this poor little kid is going to go flying off the seat. So the same thing happens in our phosphate. And so what happens is when we have ATP, okay, and we want to go through hydrolysis, so we add water, we then get ADP, okay, and a phosphate, and that extra phosphate's doing the extra energy, the work. All right, now if we were to build this back, so here's a visual of this. All right, here's our adenine, here's our ribose, these are 3 phosphates. So right now, let's go. They're 3 together. High energy bond, but a weak bond. We bring water in. Hydrolysis breaks off, and energy has happened. Energonic reaction. Energonic reaction. Now, if we were to put this back together, right? So here we're talking about the opposite of this, right? So if we have ATP, and we go this way, and we have ADP, whoops, and our phosphate. We can only do this if we have water, right? So we need water. Water needs to be here. So if we move this way, this is hydrolysis, like we were just saying, and we're breaking that apart. But we can go the opposite direction of this, and we can go the other direction. So the arrow goes this way. And these are the reactants, and that's the product. So we take a phosphate plus ADP plus, what do we need to take out? Water. When we remove the water from this scenario, we get ATP again. And this is what we call dehydration synthesis. Okay, this is from last chapter, folks. So if you don't remember this, you need to go back and look at it. We're going to talk about hydrolysis and dehydration synthesis often. Think about when we remove water from something, we are dehydrated. Now, the last portion of this little section here is the metabolic pathways. So basically pathways, meaning reactions, happen in a series. A changes to B, B changes to C, C changes to D. So we need this kind of sequential movement of metabolism within the cell. So when we're talking about metabolism, we're talking about in the cell, work of the cell. So A has to happen for B to happen for C, for D. And again, we might need energy at any one of those steps. So it might be that B needs energy, but nothing else does. And that's okay. What's really important to know is that enzymes within the cell help lower the energy needed for a reaction. So lots of times we have enzymes that play a very large role in keeping the energy levels low when our reactions are occurring. So our next video is going to go into the enzymes.